Right, let's take a look at the quadratic function, or another word we can use is the parabola. What's the standard equation that we know belongs to the parabola at this stage? Well, y equals ax squared. Remember, the x squared part is the indicative part of it being quadratic. So y equals ax squared plus c is the formula that we know at this stage belongs to a parabola, all right? What we want to do in this video is investigate what effect does the a have on the shape of the graph. What happens if that a gets bigger? What happens if it gets smaller? What does it do to the shape of your graph? As well as your c value. Okay, what influence does that c value have on what the graph looks like? So to begin that investigation, we're going to start with an absolute basic parabola, all right, as simple and as standard as a parabola can get, and that is in the form of y is equal to x squared, all right? If I were to apply the equation of y is equal to x squared to our standard equation of ax squared plus c, we want to identify, because obviously it needs to have an a value and it needs to have a c value. And what would those be if I was working with the equation of just y equals x squared? Well, the a value, remember, is obviously the coefficient in front of your x squared term. And if you don't see anything in front of it, we know by now that it's a 1 that we have in front of your a, or in front of your x squared. So the a value of the equation y is equal to x squared is 1. And the c value, which is the constant term being added or subtracted to the x squared term, well, in this case, we don't see anything, so therefore we're going to have to take it as plus 0, all right? So in its absolute basic form, my a value is 1 and my c value is 0, all right? Now we're going to take a minute to just assess what impact do those have on the shape of our graph. We're going to plot the graph and we're going to use a table of values to help us out to begin with over here. And what we've done is chosen a whole lot of independent x values, which I've started at -2 and gone through to +2. And by substituting our independent x values into the equation of y is equal to x squared, out came the dependent y values, all right? And add those then creating your coordinate pairs that we're going to plot, which will ultimately give us the shape of our graph, okay? All right, so that's exactly what we did. Where x was -2, y was 4, so that was the first point we plotted. Where x is -1, y is +1, so we plotted our next point there. At 0, 0 is our next point, 1 and 1, 2 and 4, and therefore that was how we got the shape of your y is equal to x squared. All right. Okay, so as I mentioned, that is as basic as a parabola gets. Okay, it's symmetrical about your y-axis. You can see that the graph is a perfect mirror image about the line of x equals 0, so therefore it's symmetrical, all right? And the other thing we're going to point out over here is that it's passing through your origin at 0, 0. So therefore we're landing up with the y-intercept passing through your origin at x equals 0 and y equals 0. All right. So if that's the graph in its absolute basic form, what then happens when we start playing around with the a value and the c value? Well, let's have a look and see. What if the first thing I do to my a value is I change its sign? Okay, so instead of having a graph of y is equal to x squared, which is what we have got in this graph over here, that red graph is indicating the y is equal to x squared function, okay? So if we put a negative in front of my a value, so now instead of it being +1, my a value is obviously now -1, what influence would it have on the graph? Well, what it's doing is it reflects your graph about the x-axis, so therefore folding it down, all right, and it creates therefore what we're going to refer to as a negative parabola and not a positive, all right? So the first thing we need to make sure we understand is that the sign of your coefficient of x squared, if it's positive, we have got a smiling, it's just a kind of nickname that we're going to give to this parabola. It's a smiling parabola and it's positive. However, if your coefficient of your x squared is negative, it's frowning and it's always going to therefore be facing downwards in its shape. All right, so that's the first thing we need to make sure of, is whether the a is positive or whether the a is negative. All right, then the a value itself. Okay, now we did a few experiments over here and we drew a couple of graphs just to indicate what happens to the a value when it starts getting bigger than the value of 1, all right? We drew, to begin with, that the original y is equal to x squared. This is it over here. Y equals x squared was the original graph. And remember we said that that's as standard as the parabola can get, okay, where a is 1. Now, if we start increasing that value of a, what happens to the shape of your graph? Well, let's increase it to the value of 2. So I'm looking at this function over here, y is equal to 2x squared. Now, if you were to consider substituting using a table, so in other words, I'm going to go back to this point over here. If I were to use a table such as this, all right, if I substituted an x value, say, of -2 into the equation of y is equal to 2x squared, do you agree what's going to happen to this y value over here is because there's a 2 in front of it, it's going to be doubled. So instead of being at 4, it's going to be at 8. This one over here, instead of being at 1, it's going to be at 2. So do you see how these y values are getting twice as high? Instead of being, okay, this would continue to be at 0 because anything multiplied by 0 is 0. 1 would then go up to 2, and 4 again would go up to 8. So the influence of having a 2 in front of your x squared over here is that all your y values are getting twice as high, okay? So what it's doing is it's vertically stretching your graph, all right? The 0, 0 point is remaining where it is. So that's kind of the anchor point, and all the other points are stretching up higher, causing your graph to be a little bit more narrow, all right? And this is going to keep happening. If I then multiply my x squared by a coefficient of 3, well, what's going to happen is that all the y values are now 3 times higher. So it's going to pull your graph even more narrowly, all right? If I were to go an extreme value such as 10x squared, well, from the original y is equal to x squared function, can you see that all the points are now going to be 10 times higher in terms of what the y value would be, which means it's becoming much, much more narrow and much more closely situated around your y-axis, okay? So that's what you need to understand about your a value. The greater it gets, the narrower, the more the stretch is going to be in terms of a vertical stretch on your graph, okay? What if my a value is a function or a value between 0 and 1? So we've established what happens if it's a negative. It folds down underneath your graph. We've established what happens if it's greater than 1. But what happens if it's a fraction between 0 and 1, all right? Well, just as much as if I multiplied my coefficients by 2 and 3 and so on, it got 2 times higher and 3 times higher. If I multiplied my x squared value by a half, well, then exactly the same thing's happening in that it's going to now become a half as high as what it was originally. So, for example, if this is my y is equal to x squared, if this is my original y is equal to x squared over here, at the point where x was 1 and y was 1, let's just try that again, x is 1 and y was 1. If I now take y is equal to a half x squared, where x is 1, y is now going to be half as high, so y will be at a half. So therefore pushing the graph down a little bit, and instead of stretching it, it's now actually compressing it, it's flattening it out, and it's causing it to actually lie then a little bit more widely, okay? So if I took a quarter, that would then push it down even further, because instead of being at 1 and 1, it's now going to be at 1 and a quarter, so it's even flatter. And obviously, the smaller that value, that fraction gets, the lower and lower that the y values become, causing it to flatten out further and further. All right, so that's what your a is doing to your parabola. Now let's discuss the c value, all right? The c value, and let's just shoot right back to the original graph for a second over here. Remember we said that the c value in the equation of y equals x squared was 0, all right? And when we plotted that, we established that the graph is crossing the y-axis at the point of 0, all right? Now that c value is exactly that. It represents the y-intercept of your graph. Where is it crossing the y-axis, all right? So if I increase or decrease that value of c, the influence it's having on your graph is it's either moving up or moving down the point at which the graph is intercepting your y-axis, okay? So if this graph over here, let's just do it in a different color, let's do it in green. This red one in the middle here, this is your original y is equal to x squared, where your y-intercept is obviously 0, all right? Now, if I were to then move it to, let's make it pink over here. If I said y is equal to x squared plus 1. What's happening is that this y-intercept, which was at 0, is moving up 1 unit, and it's now passing through positive 1 on your y-axis, all right? Similarly, if I then took the equation of y is equal to x squared minus 2. So instead of passing through the original value of 0, it's now going to move down 2 units. And that means that your whole graph is then just going to shift downwards. The shape, the stretch, or the compression is not being influenced over here. So it's not getting any wider or any thinner. The only difference here is that it's quite simply moving up or down. Okay, so the C value is just picking your parabola up and it's moving it up or down. All right, so that's the value of your C and the influence it has on it. Now we need to get a little bit more interesting, a little bit more technical. All right, we are now going to add another term into our standard equation. So we knew the original one, or the one we've worked with so far, was ax squared plus c. All right, and what we could establish with that right from the very beginning, ax squared plus c had a y-intercept where c is, and it was always symmetrical about the y-axis, and that's probably the most important thing to remember there. If there's no middle term, and this is what we're going to discuss in a second, but if we just have the equation of ax squared plus c, your graph is always symmetrical about the line x equals 0. That's your y-axis, all right? By adding a bx term into your equation over there, we're now going to investigate what happens when that gets added in. So we're going to start once again with the original function of y is equal to x squared, and it's this red graph over here, which, as we said, is symmetrical about your y-axis. Okay, so if we were to fold it along the line of x equals 0, it would fold perfectly on top of each side on top of each other. Now, let's take this equation over here. I am going to now take the equation of y is equal to x squared minus 3x plus 2. So you can see, obviously, we're adding a negative 3x into the equation over here. What happened to the graph? Well, look at what happened. Where it was originally as this yellow graph, it's now shifted to the right, okay? There's been a horizontal shift, all right? And essentially what the main change has happened over here is that the graph is no longer then symmetrical about the line of x equals 0. There now becomes a new axis of symmetry, because by shifting it left or right, the axis of symmetry shifts with it. All right, so we're going to discuss that in a bit more detail in a minute, but let's take a look at another example of an equation. Let's say we took y is equal to x squared plus 2x plus 1. Can you see that this graph has then shifted to the left? All right, and by shifting to the left, we're now landing up with a negative axis of symmetry that we're now going to have to find the value of. All right, so by adding in this bx term into your standard equation, the influence it's having on your graph is it's having a horizontal shift. It's adding a horizontal shift into your graph, okay? And by adding a horizontal shift, it means we're creating or developing a new axis of symmetry that we then need to find the value of, all right? So because we need to find a new axis of symmetry when we have the equation in the form ax squared plus bx plus c, what do we use? Well, we have a formula that we use to find the axis of symmetry when it is in that standard form. And this is your formula. X is equal to negative b over 2a. All right. Where does the b and the a come from? Well, remember the standard equation is ax squared plus bx plus c. So therefore the a is just whatever the coefficient of your x squared term was. The b is just the coefficient of your x term. Okay. So let's look at this equation over here. I've got y is equal to 2x plus 1. I can see that there's going to be a horizontal shift. Because it's a plus 2, it means I know that it's going to be a horizontal shift to the left. Okay, so your horizontal shifting always happens in reverse. Okay, so if it says it's plus, it's actually going to go minus and vice versa. So x squared plus 2x plus 1, I can see there's a horizontal shift. I need to determine what my new axis of symmetry is going to be. So I'm going to take the equation x is equal to negative b over 2a. where the a value in this equation, do you agree with me, is 1 and the b value is 2. So let's substitute that into our equation here. So x is equal to negative b over 2a, a being 1, and we land up with negative 2 over 2, which is giving me negative 1. All right, so the new axis of symmetry is no longer passing through the line x equals 0. It is now passing through the line x equals negative 1. All right, great. So let's just indicate on our axis, if I had an x and a y axis, and if this point over here was now negative 1, we know that the graph is now having that line there as its axis of symmetry. In addition to working out the axis of symmetry, we also need to determine at its turning points, okay? Because it's symmetrical about this line, it means that it's going to have to turn on that line over there, all right? So therefore, the x-coordinate of your axis of symmetry is always going to be the x value of your turning point, okay? So we take the value of x equals negative 1 and we substitute it into the x's of the original equation, therefore giving me negative 1x squared plus 2 multiplied by negative 1 plus 1. And if we simplify this, we're going to land up with positive 1 minus 2 plus 1, and obviously that's going to give us 2 minus 2, which is 0. So therefore the coordinates of your turning point are where x is equal to negative 1 and y is equal to 0. So if we were to very roughly plot this graph over here, what do we know? The turning point is at the point of negative 1 and 0, okay? And negative 1 being your axis of symmetry. So x is equal to negative 1 is the equation of that line of axis of symmetry. And what we also know, because we always knew that the c value, which is the constant term, represented the y-intercept. So we know the graph is going to intercept the y-axis at 1. It's a smiling graph. How do we know that? Because it's a positive x squared. So therefore, the graph would look something, but we missed that there. Let's try again. It would look more or less like that if we were to sketch it, a rough sketch of it. All right. Let's try another example over here. We've got y is equal to x squared minus 3x plus 2. A quick assessment of that equation. I can see it's a positive. It's going to be a smiling graph because your x squared is positive. I know that it's going to pass through the y-axis at 2 because that's the constant term over there. What we need to figure out is what's the new axis of symmetry and what's the new turning point, which has been created by the fact that there's a horizontal shift. Okay, so axis of symmetry, let's go. We've got x is equal to negative b over 2a, where the a value in this case was a 1 and the b value is a negative 3. Okay, so x is equal to negative b over 2a. That's giving me a positive 3 over 2, or alternatively you can say 1.5 if you prefer the decimal, as the value of x, which is your axis of symmetry. The axis of symmetry then doubles up as the x coordinate of your turning point. So therefore, to calculate the y coordinate of the turning point, we substitute x into the equation. So 3 over 2 squared minus 3 multiplied by 3 over 2 plus 2. Okay, a little bit of working out here. That's going to give us 9 over 4. This is giving us 9 over 2 and 2 over 1, which if we find a common denominator of 4, we've got 9 minus 18 plus, that's going to be 4 times by 2, which is 8. And what are we getting over there? So we've got negative 9 plus 8, which is giving me negative 1 over 4 as the y coordinate of your turning point. So therefore the turning point of your y coordinate will be where x was 3 over 2 and y is negative 1/4. And then from there you can plot those points and you're able to sketch it. All right, we're going to practice doing a lot more of that in the videos to come, so make sure you stay with us. But join us in the next video where we start discussing a different format that we can see the equation in and how we can use that equation to determine points on our graph. So I'll see you there.